So, imagine you've got these incredible organic molecules just rotating in 3D space right in front of you. You know, you'd see all these complex shapes, branching arms, rings, the whole shebang. But the actual foundation of all that wild architecture? It's the carbon skeleton. But here's the billion-dollar question. How do we actually see this hidden framework when we literally can't just stick it under a normal microscope? Well, welcome to this explainer on carbon-13 nuclear magnetic resonance spectroscopy. Now, I know that sounds like a mouthful, but it's a completely revolutionary technique. It's honestly one of the most important spectroscopic tools we have today for figuring out the intricate carbon frameworks of organic compounds. We're going to dive right into exactly how chemists use literal magnetism and radio waves to decode these deep structural secrets. Okay, here's our quick roadmap for today. We're going to hit the carbon detection challenge, jump into the principles of magnetic resonance, peek inside the spectrometer, compare carbon and proton techniques, and finally learn about reading chemical shifts.
All right, kicking things off with Section 1, the Carbon Detection Challenge. Because honestly, trying to find these carbon signals, it's kind of like looking for a needle in a massive haystack.
So our biggest hurdle right out of the gate comes down to isotopes. Take carbon-12. It's the most common isotope by far, right? It has an even number of protons and neutrons. But because of that perfectly even pairing, its spin quantum number is exactly 0. That means it is completely 100% NMR inactive. It's basically a ghost to our machines. So that leaves us relying entirely on its cousin, carbon-13, which actually has an odd number of neutrons, giving it a workable nuclear spin of 1/2. But here is the absolute kicker. In nature, only about 1.1% of all carbon atoms are carbon-13. The other roughly 99%? Yeah, that's our invisible ghost, carbon-12. Just think about what that means in practice. If you have a sample with 100 carbon atoms, statistically speaking, only one single atom is actually going to be a carbon-13 nucleus that can give us a signal. So we are working with an incredibly tiny number of targets here.
And it actually gets tougher. Not only is this natural abundance incredibly low, but carbon-13 also has a much smaller magnetogyric ratio compared to a regular proton. Put those two massive hurdles together, and the carbon-13 signal is staggeringly weak. We're talking like 10,000 times weaker than the signals we get from hydrogen atoms in standard proton NMR. It's wild.
So, moving to Section 2, Principles of Magnetic Resonance. If the signal is literally that weak, how do we force these ultra-rare atoms to show themselves? Well, it all starts with manipulating their quantum properties. Because those rare carbon-13 nuclei have spin, that spin naturally generates a tiny, inherent magnetic moment. So what do? We drop our sample right into a massive, super strong external magnetic field. This essentially forces every single carbon-13 nucleus in there to act like a microscopic compass needle, aligning itself perfectly with that powerful field. And then, it just waits to be energized. Let's break down how this actually happens in real time. First up, step 1. We blast that aligned sample with a short, incredibly powerful radio frequency pulse. This burst of energy literally tilts the magnetization vector of the spins totally out of equilibrium. Then, step 2. The moment that pulse ends, those excited nuclei start to precess and relax, basically falling back to their comfortable, lower energy state. And finally, step 3. As they relax, they let out this decaying, oscillating voltage. That right there is our signal. We call it the free induction decay, or FID for short. Okay, let's jump into Section 3, inside the spectrometer. We've got this physical signal from our microscopic magnets, but now we need the hardcore hardware that actually captures it. At the absolute heart of a pulsed Fourier transform NMR spectrometer, the little sample tube sits directly inside a constant superconducting magnet. And wrapped right around that sample is a super specialized coil. Now, this coil does double duty. It fires off that initial radio frequency pulse we talked about, and then it immediately acts as a pickup coil to listen for that oscillating electrical FID signal as the nuclei relax. And these incredible machines are a sight to see in a modern university or research lab. The main piece is this huge cylindrical tank that houses the superconducting magnet itself. And to keep that intense magnetic field perfectly uniform, the internal coils have to be constantly bathed in liquid helium and liquid nitrogen. I mean, we are talking about a very serious, highly demanding piece of hardware here just to uncover these molecular structures. But here's the thing. The raw signal that this machine picks up, that free induction decay, is honestly just a chaotic, overlapping mess of waves decaying over time.
To actually make sense of it, the attached computer uses a really complex mathematical operation called a Fourier transformation. This mathematical magic basically untangles that messy time-domain FID signal and turns it into a super clean, totally readable frequency domain spectrum where every single unique carbon environment pops up as its own distinct peak. And I really cannot overstate how huge this was. This computational leap, it wasn't just some minor software patch. It literally won a Nobel Prize. Richard R. Ernst actually took home the 1991 Nobel Prize in Chemistry because his incredible work on Fourier transform NMR is exactly what made analyzing these insanely weak, noisy carbon-13 signals a reality for chemists everywhere.
Which brings us to Section 4, comparing carbon and proton NMR. We really need to benchmark this method against the classic technique most chemists learn first. Looking at the stats side by side, the natural abundance difference is honestly wild. You've got nearly 100% for protons versus just a measly 1.1% for carbon. But take a look at the spectral window. While your typical proton spectra are squeezed into this tiny 0 to 13 parts per million range, carbon-13 stretches out over a massive 0 to 220 ppm range. Just a quick heads up though, unlike proton MMR, the peak integration in carbon MMR isn't usually proportional to the number of atoms, mostly because of differing relaxation times and other enhancement effects.
And remember those distinct magnetic properties, specifically that signal being 10,000 times weaker? That's exactly why carbon-13 analysis absolutely depends on that Fourier transform technology we just nerded out over. But hey, there's actually a silver lining here. Because carbon-13 is so incredibly rare, the odds of two carbon-13 atoms randomly sitting right next to each other in a molecule practically zero, which means we don't have to deal with homonuclear carbon-to-carbon splitting at all. It saves us from an absolute nightmare of overlapping signals.
All right, home stretch. Section 5, reading chemical shifts. Let's pull all this physics, math, and tech together and learn how to finally read a molecule's carbon skeleton. So, the exact position of a peak on the x-axis is what we call its chemical shift, and this shift depends entirely on the specific electronic neighborhood surrounding that individual carbon atom. If a carbon is tucked inside a dense cloud of electrons, it's what we call shielded from the magnetic field, and it's going to show up on the right side of the spectrum. But if nearby electronegative atoms strip those protective electrons away, well, the carbon becomes de-shielded and it gets dragged all the way over to the left side.
We actually map out these shifts. It's really cool. Your simple, highly shielded alkanes sit nice and cozy on the far right, between 5 and 45 ppm. As you move left, you start running into alkynes, then alkenes and aromatics. And finally, way over on the far left, you have your highly de-shielded carbonyl carbons from things like ketones and aldehydes. Because they're double bonded to oxygen, they get shoved all the way out into that 190 to 220 ppm territory. In the real world, chemists actually rely on super detailed reference tables to match the chemical shifts of their peaks to these established ranges. It's like having a cheat sheet. This lets a researcher look at the data and definitively reverse engineer the structural environments of absolutely every unique carbon in their sample, snapping the whole molecular puzzle together.
The real takeaway here is that, yeah, a carbon-13 experiment might take a lot longer to run just to get a decent signal-to-noise ratio, but that massive 220 ppm spectral window, it is incredibly forgiving. It spreads all those signals way out, preventing the peaks from bunching up on top of each other. The result is a spectrum that's vastly cleaner and way more distinct than your typical hydrogen mapping.
This all points to a fundamental truth in analytical chemistry. While proton NMR is fantastic for giving us the fine details about hydrogens, carbon-13 NMR hands us the most direct, unambiguous blueprint of the molecule's core framework. And because we usually decouple the protons to strip away those messy splitting patterns, every single unique carbon gives us exactly one crisp, clean peak. It's beautiful, really.
We've seen how overcoming a tiny 1.1% natural abundance and a super weak magnetic moment ultimately allowed us to map the very backbone of organic chemistry. And honestly, it really leaves you wondering, doesn't it? If we can use massive superconducting magnets and the sheer math of Fourier transforms to perfectly decode this tiny, rare isotoptic anomaly, what other completely invisible quantum phenomena are out there, just waiting for us to tune in and listen? Thanks for hanging out with me for this explainer, and definitely keep exploring the science hiding just beneath the noise.